welcome to the deep dive. We're jumping straight in today with something pretty big happening in the Ruby world.
Yeah, the integration of ZJIT.
Exactly, ZJIT. It's a brand new just-in-time compiler being merged right into Ruby itself, not just some small tweak.
No, definitely not. And we're basing this discussion mostly on a blog post from one of the developers actually working on it.
Oh, nice. So like an inside look.
Pretty much, yeah.
Yeah.
Gives us a really good view of what this new compiler is all about.
Okay, so for anyone maybe not super deep into compilers, a JIT just-in-time compiler, what does it do? It basically makes code run faster, right?
Yeah, essentially. Instead of the computer just reading code line by line, the JIT translates parts of it into the machine's own language while the program's running.
Like translating on the fly.
Exactly. And Ruby, it already has a JIT called YJIT.
Right. YJIT's been around a little while, shown some good speed-ups.
It really has.
Right.
Which leads to the big question we want to tackle today. Why ZJIT? Why bring in another JIT?
Good question.
So we'll dig into how ZJIT is different, what it might offer performance-wise, and what the plans are. Trying to keep it clear, without getting lost in the weeds.
Sounds good. So, okay, ZJIT, who's behind this one?
It's a team effort. Maxime Chevalier-Boisvert, Takashi Kokubun, Alan Wu, Max Bernstein, Aidan Fox-Ivy.
Oh.
And what's really interesting is this is the same core group that build YJIT.
Oh, wow. Okay, so they know their stuff when it comes to Ruby JITs.
Definitely. They're bringing all that experience to this new project.
And this wasn't like a long-term secret project then?
No, not really. Development seems to have kicked off properly at the start of this year.
Just this year. Wow.
Yeah, and moved fast. It recently got the green light from Mats.
From Mats himself, Ruby's creator. That's significant.
It is. Shows some real confidence in the direction.
But we should stress, it's still early days for ZJIT, right?
Yeah.
It's not like production ready tomorrow.
No, absolutely not. It's in Ruby now, which is huge, but very much in the initial stages. Lots of development still needed.
Okay, so let's get into those differences then. Architecturally, how does ZJIT stack up against YJIT? What makes it tick differently?
This is where it gets really interesting, I think. A key difference is how they handle the code internally during compilation. Compilers use something called an intermediate representation, or IR.
An IR, like a temporary format?
Sorta, yeah. Think of it like a middle language, easier to analyze and optimize before you generate the final machine code.
Okay, so what kind of IR does each one use?
YJIT goes pretty directly from Ruby's bytecode that's called YARV into a low-level IR, or LIR.
Low level, so closer to the machine.
Yeah. ZJIT takes a different path. It uses a high-level SSA-based IR called HIR.
High-level IR and SSA. That's static single assignment.
Right. It's a property of the IR that makes certain kinds of analysis and optimization a lot simpler. ZJIT is built more like a textbook compiler in that sense.
Okay, so high-level versus low-level IR. What does that mean in practice? Like, what's the impact?
Well, a high-level IR, like ZJIT's HIR, it keeps more of the structure and meaning of your original Ruby code. Okay.
Whereas the low-level IR is much closer to the raw processor instructions. Another big difference is the chunk of code they work on.
Chunk of code.
Yeah. YJIT compiles things called basic blocks. These are like short sequences of code with no jumps in or out.
Right, straight lines of code.
Pretty much. ZJIT, on the other hand, compiles an entire method all at once.
Oh, okay. So YJIT is like optimizing maybe sentence by sentence. ZJIT is looking at the whole paragraph.
That's a great analogy, actually.
Right.
Yeah. It gives ZJIT's optimizer potentially more context to work with.
Interesting. Any other key differences?
Yeah, how they figure out data types. Ruby's dynamic, right? So types can change. YJIT uses something called lazy basic block versioning, LBBV, to profile types as it goes.
Learning on the fly.
Kind of. ZJIT looks back at historical type information gathered by the interpreter before it compiles.
So ZJIT uses past behavior. YJIT learns more in the moment.
Roughly, yeah. And ZJIT has this distinct optimizer pass that works on the high-level IR. YJIT mixes optimization more into its process of lowering the IRV to LIR. Got it. And you mentioned ZJIT is more like a textbook compiler. Why did they choose that approach? The blog post mentioned it.
Yeah, and this is quite strategic, I think. They deliberately chose a more traditional compiler structure, distinct phases, the HIR, to make it potentially easier for others in the Ruby community to understand and contribute.
That makes sense. Lowering the barrier to entry.
Exactly. A more standard design might feel more familiar to people who've studied or worked on compilers before. Could be really good for the long haul, getting more eyes and hands on the project.
Yeah, fostering that community involvement.
Yeah.
Smart. Now, what about trade-offs? These different designs must have pros and cons.
For sure. YJIT's approach, working with smaller blocks and that lazy versioning, might be really good for certain kinds of fine-grained optimizations that span across different methods, maybe into procedural stuff.
Okay.
ZJIT, because it looks at the whole method and uses that HIR, gives its optimizer a much wider view of the code within that single method.
So potentially better optimizations within a method, but maybe different strengths when looking across methods.
That could be one way it shakes out. Yeah, different strengths, different potential sweet spots.
Okay, let's maybe trace the journey of some code through ZJIT then. The blog post gives a kind of overview, right?
It does. High level, it's like this. Your Ruby code gets turned into YRV bytecode first. That's standard Ruby.
Right.
Then ZJIT takes that YRV, translates it into its high-level IR, the HIR,
Okay, step 2.
and that HIR goes through optimization passes, and finally, ZJIT spits out the machine code for your processor.
YRV to HIR to optimized HIR to machine code.
Got it.
The post uses a simple add function example, add.rb. Let's start there with the YRV bytecode. What does that look like?
So for a simple add left-right, the YRV involves getting left and right onto a stack, basically. Then you hit an instruction called opt plus.
Opt plus. Optimized plus. What's special about that?
It's not just add, it's got fast paths built in, especially for adding two small integers, what Ruby calls fixnums.
Ah, so it tries to be quick for common cases.
Exactly. But it also has to do what the post calls a BOP check. BOP, basic operator check.
BOP check.
Yeah, because Ruby is so dynamic, you could actually redefine how adding integers works. Like, you could change integer hashtag plus vary.
Seriously. Wow.
Yeah, so opt plus has to check if that basic operation has been messed with. If it has, it can't use the fast path. It has to do a more general method call.
So even simple addition needs safety checks because of Ruby's flexibility.
Precisely. Now, after the interpreter runs this code enough times, it might rewrite opt plus to ZJIT plus.
Adding ZJIT to the name.
Right, and this version does something extra. It records the types of the things it's adding. That type information is crucial for ZJIT later.
Ah, okay. So the interpreter helps gather type info, then ZJIT uses it to build the HIR. How's HIR different from YRV again?
Structurally, quite different. YARV is prelinear, uses a stack for data. HIR is more like a graph. Instructions point directly to the other instructions that produce their inputs. No stack needed for that data flow.
Okay.
And it's organized into those basic blocks we mentioned.
Gotcha. So what's the initial HIR for our add function look like?
Well, even after seeing ZJIT plus, the first pass HIR is quite generic. It looks something like HIR fn add bb0 v0.basic object vv0.basic object v4.basic object send without block v0 plus av1 return v4.
Okay, lots of variables there. v0, v1, and send without block.
Yeah, v0 and v1 are the inputs. Send without block basically means call the method named plus on vo, passing v1 as the argument. Notice the types are just basic objects, super general.
So no assumption about integers yet, even though ZJIT plus recorded types.
Not in this initial HIR, no. The specialization comes during optimization. After the optimizer runs, the HIR changes quite a bit.
Okay, what does the optimized version look like?
It becomes something like HIR fn add, patch point BOP define v7, fixnum, guard type v0, fixnum v8, fixnum, guard type v1, fixnum v9, fixnum, and add v7, v8, return v9.
Whoa, okay, lots of new stuff. Guard type, fixnum add.
Right. The optimizer, using that type information collected earlier, has added guard type instructions. These are runtime checks.
Yeah, for what?
They check, is v0 really a fixnum? Is v1 really a fixnum? If either check fails at runtime.
It bails out.
Exactly. It needs to jump back to the interpreter. That's the side exit we'll talk more about. But it both pass the guards.
Then it knows they're fixnums.
Yes. And then it can use the specialized fixnum add instruction, which is way faster than the generic send without block. The patch point is still there to handle that BOP redefined case too.
Ah, so the optimized HIR is basically saying, check if they're fixnums. If yes, use this super fast add. If no, or if addition was redefined, bail out.
That's the core idea, specialization based on likely types, but with safety nets.
Okay, that makes sense. So after this optimized HIR, we get LIR, low-level IR.
Yep. The HIR gets translated down to LIR. Think of LIR as like a multi-platform assembly language. It's closer to the metal, but not tied to one specific processor like by86 or ARM yet.
And its main job is?
The blog calls it superpower managing virtual registers, basically figuring out where to temporarily store values efficiently.
Yeah. And the LIR for add, the post shows some instructions.
Yeah, it gets much more detailed. You see things like frame setup, freeing down managing memory for the function call.
Standard function stuff.
Right. Then you see test instructions, doing bit checks. That's likely part of the guard type check for fixnums.
Ah, the implementation of the guard.
Exactly. And conditional jumps like JIZ, jump if 0, or JO, jump on overflow. These handle the branching, either continue with the fast path or jump to a side exit.
Okay.
Then the actual math subtract, add. Notice the fixinum add from HIR might become multiple LIR instructions, including checks for overflow.
Right, because adding 2 fixtums might result in a number too big to be a fixtum.
Precisely. And MOV instructions for moving data around. It's much more explicit about the processor level operations.
And it's just one long list of instructions now, not blocks like HIR.
Yeah, the blog notes LAR is typically represented as one linear sequence. And sometimes a complex HIR operation might just become a call to a C helper function at the LIR level.
Okay, getting closer to the hardware. And the final step is assembly, actual machine code.
Yep. The LIR is translated into the specific assembly language for the target machine, like by86 or ARM. The post shows a snippet of by86.
What does it look like for those guard type and fixnum add operations?
It's surprisingly compact. For the guard type, you see a test instruction checking the fixnum tag bit, then a J, jump if equal, to the side exit if it's not a fixnum. Super fast check.
Just a couple of instructions.
Yeah. And for the fixnum add, you see the sub, the add, and the JO, jump on overflow. Again, just a handful of basic machine instructions.
It's kind of amazing how that high-level idea becomes so few fast operations.
It really knows the benefit of that type specialization. You trade the generic call for these highly optimized sequences when the types match.
And the post says ARM code looks similar.
Yeah, the principle is the same, just different instruction names, same efficient checks, and specialized addition.
Okay, so that's the pipeline. Now, where does ZJIT stand today? It's merged, but you said it's early days. What are the plans?
Right, definitely early days. The post makes that clear. It's not ready for prime time yet. So for Ruby 3.5, the plan is actually to ship both YJIT and ZJIT.
Both, right?
Yeah. YJIT will continue to be maintained and used while ZJIT development carries on. The goal is eventually to get ZJIT up to par with YJIT in terms of features and, importantly, performance.
So what's the absolute immediate focus for the ZJIT team?
Number one priority right now seems to be implementing robust side exits.
We mentioned those.
Yeah.
The bailout mechanism when a guard type check fails.
Exactly. Making sure that when the compiled code hits a situation, it wasn't optimized for like getting a string when it expected a fixnum. It can safely and correctly hand control back to the Ruby interpreter.
Why is that so critical right now?
2 massive reasons. First, correctness. They need solid side exits to be able to run the full Ruby test suite against ZJIT. Can it handle all of Ruby's features without crashing or giving wrong results? Side exits are key to passing those tests.
Makes sense. You need it to be correct before fast.
Absolutely. Second, performance evaluation. Once side exits work reliably, they can start running real benchmarks like YJIT bench and even actual production apps under ZJIT.
Ah, to see how fast it actually is.
Right. That's when they can get real data on where it shines and where it needs more work. You can't really benchmark properly until the side exits are solid.
Okay, so side exits unlock correctness testing and performance benchmarking. What's next after that's in place?
Profiling. Once they can run real code and benchmarks, they'll need to profile ZJIT itself, figure out where the time is being spent, identify the biggest bottlenecks, and find the most impactful optimization opportunities.
Use the performance data to guide the next steps.
Exactly. Focus the effort where it matters most.
Okay, so summing up then. ZJIT is this new JIT in Ruby built by the YJIT team, but with a different architecture, high-level IR, whole method compilation.
A more textbook design aiming for community contribution.
Right, and it offers potentially different optimization strengths compared to YJIT. Still very early days, focus now is on side exits for correctness and benchmarking.
That's a pretty good summary, yeah. It's a really significant development, showing Ruby's continued push for better performance through multiple strategies.
It's fascinating to get this peek behind the scenes. You really see the complexity involved in speeding up a language as dynamic as Ruby.
It really is complex, and it leaves you, our listener, with something interesting to think about, maybe.
Oh, yeah.
Consider that fundamental tension, right? Ruby's dynamic flexibility change anything, anytime, versus the need for compilers like YJIT and ZJIT to make assumptions, especially about types, to get speed. How do you think they'll keep balancing that? And what does the future look like with potentially 2 different evolving JITs in the mix?
Yeah. performance versus dynamism,
Yeah.
and maybe two tools offering different trade-offs. Definitely something they keep an eye on as Ruby continues to evolve.
For sure. It's an exciting time for Ruby performance.